Hello everyone, and today we're going to be talking about Chapter 3, Part 2. Before that though, if you're in my Fall 2022 classes, today is the day that the Nobel Prize for Chemistry is being awarded, and so I just wanted to talk about some science news real quick. And so, the Chemistry Award this year went to, or was in the area of click chemistry. And click chemistry is an area of chemistry that chemists like to throw shade upon biologists all the time, and so they say that click chemistry is so easy that biologists can do it. But click chemistry is really important because it takes really hard processes and makes it easier, just like it says here. You take chemistry that's usually complex and takes a lot of time and energy and probably a lot of resources, and make it so simple that it takes less resources, and a lot of times it's cleaner and greener than the more complicated processes. And so that's fun. Also, since we've been talking about quantum mechanics, the physics award for this week in Nobel Prize week went towards quantum mechanics. So just some fun science news. And also, I don't know if you guys have ever heard of the Ig Nobel Awards. The Ig Nobel Awards are kind of satire. It's awards that are based upon, unusual scientific questions. The science is very legitimate, but it's based upon projects that might seem a little bit silly. And so this is just something fun to go through, even if you're not a sciencey person. Like, for example, I really like the ones from 2019. So this is their website. And this just shows, you can go, when you scroll all the way to the top, you can see the past years. And I particularly like 2019. Does pizza protect against cancer? Let's see. Estimation of the total saliva produced per day in 5-year-old children. That was the chemistry prize. And so they award 10, I think it's 10 awards. And so I think they didn't have one for chemistry this year because maybe chemistry didn't make the cut for those 10 awards. Money in the transmission of bacteria, that's the economics prize, but that could also be biology. And so there's how wombats make cubed poo, that was for physics. And so there's a lot of really cool Ig Nobel Awards. Using saliva as a cleaning agent for dirty surfaces. And if you click on the reference, it'll actually take you to an abstract where you can read a little bit about it. So, just some fun science news, since it is Nobel week. So on to Chapter 3. And so we've talked about so far the wave-particle duality of light and the properties of waves, and the energy associated with the properties of waves. And one of the key points discovered that we'll talk about in this video, or is talked about in that video, was how frequency, the higher the frequency, the higher the energy, right? So how did we figure that out? And how did we figure out the wave-particle duality of light? Well, that came from the photoelectric effect. And so as we're talking about Nobel Prizes, Einstein won his Nobel Prize for an experiment called the photoelectric effect, which showed that light behaves both as a wave and a particle. And it was originally thought that it was the amplitude, not the frequency of light, that determines the energy. And this was not necessarily an unreasonable assumption, because we now know that the higher the amplitude, the brighter the light. When you compare lights of a higher amplitude, when you compare waves of a higher amplitude that have the same wavelength. So if it has the same wavelength, but the amplitude, that point from the resting point to the peak, is higher, the higher the amplitude, the brighter the light. And so one would guess that, or one would hypothesize that if the light's brighter, then you have more energy. But it was found through these experiments that the frequency of light determines energy, and it also was Einstein's way of discovering that sometimes light behaves as a wave and sometimes it behaves as a particle. And so that's what these two videos talk about. This talks about more of an overview. This goes into a little bit more detail. And these are only like 3 to 5 minute videos, so it would take you less than like 10 minutes to watch them both. So the kinetic energy of photoelectrons increases with light frequency. So the energy increases with frequency, as we already know. The energy remains constant as light amplitude increases. And again, we are comparing, let me write this out, because there's a stipulation here. When comparing waves of the same wavelength, when comparing waves of the same wavelength. And we're going to pretend for a minute. We're going to do a lot of pretending that I'm actually a good artist in this class. So let's pretend that I can draw two waves with the same wavelength. Kind of the same wavelength. So but the amplitude of one is higher than the other. Even though the light is brighter, right, the kinetic energy remains the same here. Now, if I were to compare, this to this, right, this kinetic energy would be greater because my frequency is greater, because my wavelengths are shorter. And that's what I mean by the same wavelength. When your frequency changes, so does your wavelength. Okay? So, energy of the photon. When it behaves as a wave, we treat it as a wave. But when we talk about light behaving as a particle, it's made of photons. And the energy of a photon can be calculated using Planck's equation. And so I have two equations here that talk about the energy of the photon. H is Planck's constant. You're going to have a lot of constants in this class. And V is frequency in hertz. Remember, we talked about what this means, seconds to the -1, because frequency is the opposite of the period, and period is measured in seconds. So seconds to the -1 is just 1 over seconds. All right, and then here's another equation. E equals Planck's constant times the speed of light over the wavelength. And we know from previous lectures what the speed of light is. So these are two constants that are good to know. And so I've suggested already, but I suggest making a formula sheet for chapter 3 for when you take your exam. And just writing out what each equation means. And so you'll notice that this equation is simply rearranged here. Okay? Wait. I think I wrote one of them wrong. This should not be V. This should be wavelength. So let me correct that really quick. Wavelength. There we go. Because you have V here, right? We have V here. And what would V be if we use this equation here? We would divide by this, right? So V equals C over lambda, or wavelength. So we're just taking this and putting it and substituting it here to get E equals HC over the wavelength. Okay, so that's where this equation comes from. All right, so let me get rid of that. So this is just helpful to have a formula sheet for when you take your exam or you're doing problems. That way you can have everything written out. And you can have like the units and stuff also written out if you wish. Let's see. For h times c, these are both constants, and so I personally like to go ahead and just multiply them together since that's going to be the same number each time. You don't have to do that. You don't have to know the combination of these two constants. And really, your test is going to be take home, so you can have these constants written out. At this point, I'm not expecting you're not going to be expected to memorize this, because even when you take your final, I'm going to allow you to make your own equation sheet. Okay, so this is just helpful for me to make the problem go by a little bit quicker. And so, now that we have our equations, let's do a practice problem. When we see light from a neon sign, we are observing radiation from excited neon atoms. If this radiation has a wavelength of 640 nanometers, what is the energy of the photon being emitted? Alright, and so we have a wavelength, and so we have the energy of the photon is what we're being asked for. So we're going to be using this equation here, this bottom one. Okay? And you will need to convert from nanometers to meters. There's 10 to the 9th nanometers in 1 meter. And so I just started off the problem with how we're going to convert that. Okay? And so when we go back up here, alright, we're going to go through the same steps that we have been going through for word problems. What are we given? Well, we're being given the wavelength. And converting that wavelength, you have 640 divided by 10 to the 9th. I have my calculator. Get that in real quick. 640 divided by 10 to the 9th. And you're going to get some scientific notation, which is fine. Right? We've dealt with scientific notation before. So this is going to equal 6.4 times 10 to the negative 7th meters. So I'm going to put that here. 6.4 times 10 to the negative 7th meters. It's nice to go ahead and take care of this so that way we don't have to worry about it later. Alright, and what do I know? What do I know? Well, since it asks for wavelength, or it gives us wavelength rather, and it asks for the energy of the photon, that's how I know that I'm using this bottom equation, because that's the one that involves both wavelength and the energy of the photon. This does not involve wavelength, and this does not involve the energy of the photon. And so writing out this process will help you understand which formulas to use, particularly when you're taking your final and you have a number of word problems and you have to figure out which formula to use when you're looking at your formula sheet. And so I know that E equals HC over lambda, and then for me, I'm going to go ahead and put this for HC equals 1.986 times 10 to the negative 25th. That equals 1.986 times 10 to the negative 25th, right? And what are they asking for? Well, they're asking for the energy of the photon, right? And so I can set up my equation now. E equals HC over wavelength, and then E equals 1.986 times 10 to the negative 25th, all over my wavelength, 6.4 times 10 to the negative 7th. Alright, and we should get 3.10 times 10 to the negative 19th. And I'm going to type that in my calculator just to check. 1.986 times 10 to the negative 25th, all over 6.4 times 10 to the negative 7th. Alright, 3.10 times 10 to the negative 19th. So that's what you should get. This is just where they went they converted it within the problem. To me, that's just too much to type into my calculator to keep up with, but if you're better at keeping up with what's in your calculator and not mistyping something, I am not. But if you are, by all means, feel free to do it this way. Alright. And line spectra is just an interesting phenomenon on how astronomers are able to tell what stars are made of. And so, if we're going to go to this website, right? And this just tells us about how astronomers are able to use spectroscopy to figure out what planets are made of. Because how do you figure out that a planet is so much percentage of oxygen when it's so many million or thousand whatever light years away? And so they take these spectra, and there's different spectra for different elements, and they use that information to figure out the percentage of what planets are made of. And this is more of a physics thing. I don't understand it to a great degree, but it's just simply interesting to know how they can look through a telescope and be able to tell how much of an element a planet is made of. And so they look at a target star, and the light from the sky, hits the telescope, and then they get this spectrum, right? And from that spectrum, they can tell what percentage of elements, the element percentages of each planet. And so that's just an interesting real-life application of light and how light can help us understand, not just see the things around us, but to understand what the things around us are made of. Okay, and so we've talked about the wave-particle duality of light. Now, as we mentioned in the previous lecture we had, light is part of the electromagnetic spectrum, and the electromagnetic spectrum as a whole has this wave-particle duality. So this classic model of how electrons are located around the atom is very oversimplified. It's a little not as straightforward as that. It's not as straightforward as, the pictures we've been seeing where you have the nucleus, right? The nucleus that's made up of your protons and electrons, and just, these what's referred to as shells, with your electrons around it. It's not quite that simple. This is a good starting idea to understand like energy shells, but really we don't exactly know where electrons are. There's like a probability it could be here or here or here. And being able to say and to narrow down that probability is what orbitals and the concept of orbitals are for. Orbitals are not a straightforward idea at all. It's a bit much to try to wrap your brain around, but we're going to walk through it step by step. But just know that most professors I've ever had that talk about this model of orbitals, they all theorize that the people who came up with this were on drugs, and you will see why. Okay? And so, what we talk about in this section has a lot of videos because, as you can tell, I'm not an artist, and these people who made these wonderful videos, who are also much smarter than me, are also better artists than me, which most people are anyways, but are better artists than me. But that's why there's a lot of videos in this chapter, because there are other people who can because we're really talking about 3D things, and they have like the software and the art skills to be able to show that 3D-ness a whole lot better. And so, really, orbitals, what are they and how they work? So first of all, we're going to talk about how electrons are located within shells, and then within those shells, the probability of them being in a particular orbital that's in a shell. And so, the diagram of these shells, excuse me, I'll try to draw it a little bit better this time. This is the nucleus, so I'm going to put an N, not for neutron, but for nucleus. This is the nucleus. And then you have shells that surround this nucleus. And the higher the shell, the higher the energy. So we'll say this is the first shell. And we'll say this is the second shell. Excuse me. So, sorry. So, the closer to the nucleus the shell is, the lower the energy in terms of shells. Alright. And further away means you have a higher energy. Further away means you have a higher energy. And so our shells, which is the view you're used to seeing, this right here, they don't really tell us where they are, they just tell us what the energy is. And so within those shells or orbitals, and the orbitals are more indicative of the actual location of an electron. Because quantum mechanics says that you can never know exactly where an electron is at a given moment. But you can figure out kind of like where it might be. So a shell is like the floor of an apartment complex where the electron lives, whereas the orbital is the actual apartment itself, where the electron resides. And you can think about this analogy a little bit further and think about all the electrons are under house arrest. They have to be within this apartment complex. They can't just be anywhere in the atom. They're restricted to their particular apartments or orbitals. They have to stay in those orbitals. But in quantum mechanics, you can't just open the window and say, oh, there you are, electron. Like, it's like all the windows and doors are closed, so you can never peek in for sure to know where it's at a given moment. And so the shapes of the different apartments or orbitals are different. And that becomes important when you talk about certain types of bonding, which we're not going to, that's more of an organic chemistry thing. This is just to give you an idea of orbitals and just introducing it. And so, what do these orbitals, each of these shells have these orbitals. And so these orbitals look like this. So you have your s orbital, you have your s orbital, s orbital. You have your p orbital. So you can kind of think of these as, you know how you can get different types of apartments on different levels that are nice. Some are nicer, some hold more than others. You can think of the s orbital as like that studio apartment. You know, it can only hold 2 electrons, so it can only hold 2 people. But when you talk about the p orbitals, right, you have 3 p orbitals, one for each plane of symmetry. So you have an x, y, and z. They do 1, 0, and -1 in this picture. And for d, it can hold even more d orbitals. And then we have f orbitals. Right? And so, if we talk about these energy shells, going back to that idea, the different shells can hold different numbers of electrons because they have different numbers of orbitals. It's like if you had a floor that had only 1 or 2 apartments, because that ground floor has like the office and all the stuff in it, so it only has 1 or 2 apartments. But then as you get higher, you have your second floor that can hold 4 apartments or 3 apartments and things like that. And so as you get higher, the higher the energy, the higher the shell, the more electrons that particular shell can hold because there's more orbitals located within that shell. And so when we talk about the let's talk about that first shell. So let's talk about that first shell. And why it can only hold 2. That first shell with the lowest energy, so this is my nucleus, right? It's my nucleus. And then that first shell only has a 1s orbital. I'm going to put 1. A lot of times it says N for this shell. I don't know why, lowercase n. So 1N can hold 2 electrons. Because you have only one s orbital. S orbital looks like a sphere, and it can hold 2 electrons. S orbital. And that's all for that first shell. Now, if we talk about that second shell that has 2N, so it would look like you have your nucleus, and then your first shell, and then your second shell. Alright, so we talked about the first shell can hold 2 electrons. The second shell can hold 8 because it has an s orbital that can hold 2. And then it has 3 p orbitals, and they look kind of like dumbbells. Let me try to draw that a little bit better. There we go. And you have 3 of these, and each of these can hold 2. And you have your p orbitals. You have 3 p orbitals. Alright, and that can hold 2. The s orbital can hold 2, and this can hold a total of 6, 2 for each of these orbitals, which makes 8 electrons in that second shell. And so as you go higher within these shells, you'll have more and more of these orbitals, and because you have more of these orbitals that can hold 2 electrons each, then you're going to start having more electrons that can be held within that shell, and that's why it goes higher with this specific pattern. Okay? And so this is just an explanation, a written out explanation of what I just said. Each orbital can hold 2 electrons, which is why the first shell can only hold 2 electrons, because it only has that 1s orbital. The second shell has 2 subshells, and each subshell is talking about a type of orbital. It has 2 subshells because it has orbital. Because it has an s orbital and 3 p orbitals, right? But this is just 2 different types of orbitals, and that's why it has 2 subshells. We're not going to be getting too much into subshells, but in case you watch the Khan Academy videos about subshells, I wanted you to understand where that was coming from. And so this would be a subshell, and this would be a subshell. Okay? But then within those subshells, you have these individual orbitals. And as we go higher, and we'll talk more about it the next class period, I don't want to put too much on you now because I realize this is not a straightforward concept, and so I want to give your mind some time to wrap around it before we get into specifically orbital notation. But this is just why those shells fill up in this particular pattern. It doesn't seem like it has a mathematical pattern, but it's actually 2n to the 2, and the n is the shell number. Okay, and so if you have the first shell number, 2 times 1 to the power of 2, comes out to be 2 times 1 times 1, and that's 2, right? And so if I had 2 times 2 to the second power, right, then I'm going to have 2 times 2 times 2, right? And that's going to give me 8. electrons. And so this is the formula that shows this pattern, and this formula stays consistent through at least the first 4 shells. Okay? And so we have a little bit of math in here, but really what explains this math is how the orbitals are arranged within each shell. All right? And I'm going to leave you there to kind of be able, for you to be able to kind of like wrap your mind around this stuff.